Okay, everybody, this is going to be our first trial online video lecture. So let's try this out, see how it goes, and I'm really looking forward to your feedback on this, okay? So I'm going to solve the in-class example from Tuesday. We have a beam here, and we're going to use the conjugate beam method to solve for the displacement of the pin at B and also the slope of each beam segment connected to the pin. Okay, so the first thing we want to do here is let's use the method of superposition. Okay, so I'm going to write that down here. Okay, and if you don't remember what superposition is, all it is taking some complicated system and simplifying it by adding less complicated systems together. So for example, I can say that this beam is actually equal to a beam with just the 8 kip load here plus a beam with just the 30 kip foot moment applied at the end, but I need to also add in that reaction from the roller, or else I'd have to take it out every single time and recalculate it. So I can consider this to be a cantilever beam, get rid of that. And of course, I still have this internal hinge here, so I'm not getting rid of the internal hinge. I'm kind of just ignoring it for now, okay? So I'm going to create a moment diagram. I'm going to call this first beam number 1, number 2, and number 3, and I'm going to draw 3 moment diagrams, one for each of these beams. And then of course we know we're applying, for conjugate beam method, we're applying the moment diagram. I'll write that right here. M over EI as load. Okay, that's what's happening here. Okay, so let's start with number 1 here. Number 1, we have this beam. We're going to find the moment due to the 8 kip load. I still have a hinge. I'm treating this as a cantilever, so I'm ignoring that end reaction. I'm going to save that for number 3, remember? So all I have to do here is determine the moment on this support. Let me write it here. We have an MA. We, of course, do have these other reactions here. Okay. And if I continue with this, by some moments, about A, this was 12 feet away. I just get MA is equal to 96 kip feet. Okay. And now I can draw the moment diagram. Okay, you could see, I'll actually draw the shear first, okay, so we can see the AY is going to be equal to 8 kips too, so I'll go up 8 kips, and then I'll have no change. I'll be pushed down 8 kips. So this is my shear in kips. Okay, now it's a lot easier to see what the moment's going to be here. If I have a straight line here for my moment, I know I'm going to have also a straight line, but not constant. Now it's going to be linear, right? So I'm going to start here at negative 96, the moment that I have right here, and then I just have to draw a straight line up to 0, and that's going to be my first loading diagram. Okay, I'm going to do the same thing now for number 2 in superposition, and I'm going to redraw this beam. Okay, here is a hinge. I'm only considering the 30 kip foot. Okay, and I'm going to also have these reactions again. And you can already see how much easier this is than what we were trying to do in class. So I'm glad you guys went through that process of trial and error. Okay, because you can still continue to try to do it that way, but this is just so much easier. So superposition really, this process just really simplifies our life. Simplifies calculations. Okay, and that's why we do it. As long as we're adding in everything happening to the beam, then it's all fine. We're adding everything back in. This is like saying 1 + 1 + 1 is equal to 3, and we're all good. Okay, so number 2 here, again, you can see that if we have a 30 kip-foot moment applied at the end of the beam, MA is just going to be equal to 30 kip feet. And I can directly draw the moment diagram. You can draw the shear if you want. We have nothing happening. I'm just going to directly draw the moment diagram. And all we have here, we are starting at -30, constant, we get pushed up. And this is my second loading, okay? And then for number 3, take the third part of that element for superposition. All I have is that reaction CY. Okay, and this we had calculated as 2 kips. So you can come here initially. I'll show you how you get that. You come initially to the beam. We have these 3 reactions. And we have CY. And if we make a cut here, okay, what we're doing, I'll draw it right here, is we have this side of the beam, this is the hinge, this part I'm breaking up, right? And at the hinge, we have a BX in this direction. The other side has equal and opposite BX, okay? We have an AY, an AX, an MA. I'll call this BY. That means we have an equal and opposite BY. And then, of course, we have a CY. And then we had an 8 kips applied here. And we had a 30 kip foot moment applied at the end here. Okay, so now we can start from this side here. And we can calculate CY that's equal to, if we just sum moments here, this is 15 feet. And we get CY is just 2 kips. Okay. And now here, if we come back, we can apply that 2 kips. Okay. And once again, let's calculate what that 2 kips does to our moment diagram. Okay. So if this is 15 feet and this is 24 feet, right? If I sum moments about A, set them equal to 0. I have +2 times what's 24 plus 15? 39. Okay. And then plus MA equals 0. I end up getting MA is equal to -78, which just means that it's the opposite direction of what I drew. So I'm going to come here and correct that and say this is not the right direction. It's actually, this is the correct direction, and it's going to be a 78 kip foot in that direction, okay? Now when I come to my moment diagram, right, I do have a 2 kip load from the AY. So now my moment diagram, I'm starting at this +78. This is moment kip foot. Okay. And I go back all the way down to 0. And all I have to do is connect the, that point is really messy. Let me see if I can go back. Well, that's a straight line, right? Okay, so connect those 2 points to the straight line. And now I have my third moment diagram, okay? And to convert these, so I'm going to circle the 3 moment diagrams so we can see all of them. Okay, this is 1. This is 2. And you can see how simple these loadings are now, right? Now, all I want to do to convert these to moment curvature is divide by EI, divide by EI, divide by EI, and now I have my loading for my conjugate beam. Okay, so I'm going to take all those loads. I'm going to redraw my beam down here. Okay, and I'm going to put the 30 distributed load like this, and it's negative, so I'm going to draw the arrows going down. Okay. And then I'm going to apply also, I'll draw in a different color, I'll apply the 96, which is also negative. Okay, you can kind of apply it however you like. It only goes to 12 feet. So let's say that here to here is 12. I'm going to draw the 96 kind of on top of that like this. Okay, so let me put this back in pink. This would be the 30 kip per foot. The blue one is the 96 kip per foot. And then we have the positive 78. Okay, and that one's going to be going in the positive direction, so the arrows should go up. Okay, this is going to look kind of funny, but really we can treat them all separately. So then we have a third, kind of if this was the beam. Okay, and they're going in this direction. And this is the 78. Okay, so this is now our conjugate beam. And actually we need to add our supports in, so you can see we had a fixed support, so now it's free. We're going to have a roller on the end here, and we still have that hinge. Okay, and now what we can do is we want to sum the forces just to the right of B and just to the left of B, because the question asks for the theta right before and right after, right? So we need to sum forces right before point B, which would be somewhere right here, and right after point B, and see what we get there. Okay, so let's start by making that cut. Okay, so let's come here. This is gonna be, I'll call this cut 1 and cut 2. So I'm gonna make that cut 1, and all we'd have that distributed load, and we would have that small portion of the triangular load. Okay, so I'll try to draw it like this. We have the distributed load pulling down, it's negative. Actually, let me draw it in pink so we can keep the corresponding colors. So we have the distributed load, this is the 30. Okay, and then we have the positive, we have the positive one that we drew in green, and that's going to be some portion of the load kind of like this, right? Okay, and now we have here some shear VB. I'll call this, not that symbol, I'm not sure what that is, VB, and we'll say this is VB from the right side. Okay, I'm going to put a little prime, which means that we're dealing with the conjugate beam. And then we have moment B prime. Okay, and we have some resultants that we can get here. So here we're going to get 225 over EI, right? Here we're going to get 450 over EI. And then we have this reaction from the roller of 3.6 over EI. Okay, and we can sum forces in the y direction, set them equal to 0. Okay, and we'll get VB prime, conjugate beam to the right, plus 225 over EI minus 450 over EI minus 3.6 over EI equals 0. And we end up getting VB prime to the right is 228.6 over EI. And if we plug in the EI that was given, we get 0.0378. And really we know that the shear for the conjugate beam is just equal to the rotation for the real beam. So this is the rotation at point B from the right, and we have 0.0378 radians. Okay. And then we can continue this and take our second cut now, just to the left of B. So this is cut 2. Okay, and I'm going to draw the same thing. Put our distributed load in pink at the bottom here. Okay, put our triangular load in green at the top here. Okay, and this one was going up, it's positive. Okay, and we have our resultant, something like this here, of again 225 over EI, and then we have our 450. Okay, and then we have here our 3.6 again. Okay. And now I want to find this MB and VB to the right. Sorry, to the left. Let me draw that in. So VB conjugate beam to the left, and of course this MB prime again. So if I sum okay. Then I'm going to get this negative MB plus 225 over EI times 5 minus 450 over EI times 7.5 minus 3.6 over EI times 15, and I can get that MB equals negative 2304 over EI, and if I plug in E and I get negative 4.58, and we know that MB for the conjugate beam is really the displacement, the vertical displacement of the real beam, so I have 4.58 inches. Okay, now, so this might look confusing. This is not cut 2, this is just the summation 2. So I'm going to take out the 2 here. This is a summation 2, so the first one was a summation for shear. This one was for moment. Now we're going to take our shear right after, just to the left, so sum forces just to the left of B prime, okay? And if I do that, I would get this VB prime to the left plus that 228 okay, that I just got from the right here, because now the right gets to be included, right? This is, let me write this. This is VB prime to the right, okay? This is the only addition here. I'm now just including that pin, or that internal hinge. Everything else stays the same, okay? And I can get VB prime to the left now is actually equal to 0. This all cancels out. So I end up getting that theta B at L is 0. Okay. And this is the solution. Okay.